How are you, Elvin?
Hi. Hey, Hisham. Hisham, hi. Good.
Uh,
How are you?
Nice to
Nice
meet you,
to
my
meet
friend. You know, almost 90 people accepted the invitation.
you. Nice.
It sounds like it is very popular topic. So usually, Elvin, we wait until 9:05 that
Uh-huh.
many people can join. I don't think all 90 people will join, but
Of
we'll
course.
see how many people will join, and then you can start. And
Sure, sure. Yeah,
and
we can.
yeah, and you can start by introducing yourself and what you do, and then you can delve into your presentation. I send your bio and I send everything in the invitation, but I would like you to introduce yourself and provide any details that you may have not sent to me before.
Oh,
So thank you very much, really, for I appreciate it. It is this presentation really had so many people interested. I am impressed.
I'm really happy to hear that, of course. And also thank you very much for this kind invite.
Oh, thank you very much. Actually, this is a series of meetings. I hold them to discuss neuromorphic computing, and it will be good idea, um, Erwin, if you can discuss the future of neuromorphic computing. What is its potential? How it can be used at a scale? Like Intel has already low-heat chips. So what happened in productizing those and what is the future trend? We need to look at the future because when I talk to some people in other presentation, they say yes, neuromorphic computing has great potential. It is the future, but they cannot really uh, quantify this or right. So we need to find out when it will be used at a scale, when it can be used to replace GPUs, for example, to in AI learning and training. You will discuss this throughout the presentation, not now, but this is some of the questions that come to people's mind.
Yeah, of course, of course. I also will try to keep I would like to keep the presentation um at least partially interactive, so when there's like critical questions I can
Sure,
also try to answer
sure.
them as much as possible.
Well, before you start, you can mention this.
Yeah, sure.
So let us wait for a few more minutes. We got 18 people now. 18 is not enough, although it is a good number, but we are supposed to get 90. It was 90 people accepted. So it is very popular, and people need to know what Intel is doing actually.
Yeah. We can wait a few more minutes.
That's great, actually. I'm glad to get hold of somebody from Intel to present what Intel is doing in neuromorphic computing because I think the lead of your group, I forgot his name.
Mike
Yeah,
Davis.
exactly. He didn't respond to my email, so I am really happy that you accepted to present.
Yeah, I'm also partially from I'm partially also involved in academia. That's why it's
Ah,
for
that's
me
good.
it's always
Yes,
good um, good event to like present
that's
my work, get feedback, hear
yes,
what people are thinking and doing. So this is
yes, I
in
agree.
general very valuable. That's why maybe. But yeah,
Yeah,
he's
but
also extremely busy, I imagine, these days. So.
yeah, the other thing is people in academia are excited about it. They do lots of research, and I invited people from research labs like Sandia Lab before. And
Hmm.
uh, so from research point of view, it is very active. We had a panel in supercomputer conference about neuromorphic computing. Does it need supercomputing or vice versa? It was interesting discussion between Sandia Labs and professors in universities, academia, and, and industry. So it is really an active. an active area of research. I believe it has strong potential, but we need to demonstrate this or show it.
Yeah, hopefully I will manage to at least
Good.
demonstrate part of
Yeah,
part of it.
and the
Sure.
continuous learning is an important subject for sure. Even in AI nowadays, we talk about how to continuously learn, which try to mimic how the brain works. Where are you now, Elvin?
Location wise, I live in Munich, Germany.
You are in Germany now.
Yes.
Oh, wow. Which university you are affiliated with?
It's LMU.
Oh,
I was both affiliated with TUM and LMU, like both two universities in Munich.
excellent. So, which city you are in Munich?
Yes, Munich.
Yeah, exactly. It's a good university, very good university.
Yeah, yeah,
One of the best.
yeah. It's one of the best in Germany. Yeah, it's a really good place.
Yeah. So we got 30 people uh, joined. That's still good number, not 90. So I wish everybody who accepted will attend, but you can start now, Elvin, and more
Yeah,
people will join later,
sure,
Go
sure,
for
sure.
it.
Yeah, thanks again for this kind invitation, and I also already want to thank everyone who is here today um, to listen to this talk. My name is Elvin. Uh, I am a neuromorphic computing researcher at Intel, but also in LMU University in Munich. So I am basically graduating from my PhD very soon, in a few months. So I will present today um, some of my PhD work, but also in general, as Hisham was mentioning, like the potential and the future of neuromorphic computing, mainly from the learning perspective. So
Excellent.
that is my expertise and that's my interest. So I will try to go over those. Let me maybe share
Before you
first
start,
my
please,
screen.
everybody mute yourself unless you would like to speak, in which case you can raise your hand.
Yes, also I would like to keep the presentation at least partially interactive. So when you have really burning questions or something is very unclear, please stop me or raise your hand. I'm happy to answer the questions during the presentation too. So let me share.
I want to mention that we had Brad Imoni, who is really a great neuromorphic computing scientist in uh,
Hmm.
in Sandia. So welcome, Brad.
Hi, hi. Hey, everyone.
Go ahead, El.
So, yes. So today's, you see my screen?
I see it very well.
Okay, good. So, title of today's talk is real-time continuous learning at the edge, and how do we go from algorithms to neuromorphic hardware? So I will try to talk about um, co-designing algorithms, learning algorithms for neuromorphic hardware and its potential. So, uh, let me, yeah, I need to show, as usual, some legal information about from Intel. But the main thing I want to start with is that today I have one, let's say, primary goal, and that is to convince the, um, the audience here today for two things. One, that many applications, today's and futures, need real-time adaptive AI. And I will elaborate more on that. What does this really mean? But in short, it is uh, trying to achieve human-like learning that is continuous over time, life learning and adaptive. So this is, and I believe this this will many applications will need such learning and such adaptivity. So this is the first thing I want to convince you today. And the second related thing
Are
is,
you guys going to record this? Yeah. Okay.
Yes, it is recorded, and Elvin will also send me the slides. I will send
Awesome.
both the recording and the slides.
Awesome. Thank you.
great. Yeah. So I was mentioning the second thing that I want to convince you today is that this type of AI, this adaptive AI, will need novel learning algorithms and specialized hardware. So of course you imagine that by specialized hardware I point to mostly neuromorphic, but it's also not only in that regard neuromorphic. So let's get going. Starting with the first point, many applications need real-time adaptive AI. What do I? Oops, oh, I jumped to the end by mistake. Sorry. Okay, so what do I mean by that? I want to start with mentioning the critical challenges of modern edge AI system to give you a bit of context, in which cases the learning will actually be needed. The challenge is how to adapt to open world environments when you deploy an AI agent, an adaptive system. This could be a drone, this could be a robot, this could be any type of AI system deployed in the real world, where the data distributions shift, new classes emerge. So how do we adapt to this kind of real world environments while also adhering to swap constraints, meaning that energy, computation, memory, latency, these are limited. And if you look at offline training, it's very well known that when you train a network on no matter how big of a data, there is going to be always situations and environments and cases where this network doesn't generalize to it as well. So generally, you need some kind of continual adaptation, like ongoing learning, adapting to changes. This is framed under continual learning, lifelong learning type of literature mainly. But the goal is simple: adapt to environment as it changes, and don't forget your previous knowledge. So where is this needed? So as I said, drones deployed for agriculture, for infrastructure inspection, for many use cases, because they will always encounter different environments, different objects, different weather conditions. We cannot try, I think it doesn't make so much sense to try to collect as much as data possible just to cover any possibility in the world. I always say that if you try to model the entire universe, you need a universe. Same thing goes for humanoid robots that is on rise this last few years. Of course, they are also deployed in dynamic environments. AR, VR glasses as a consumer product also requires this kind of adaptivity, and many other applications like predictive maintenance in the factories, etc. So there are many applications, just few of them here. But what I really mean with the learning in this case is a bit more specific. So I would like to show you quickly the spectrum of learning paradigms, because there are many in the spectrum. So on two edges of the spectrum, you have offline training and online learning. So offline training, you have large number of samples and you reiterate over this data many times. While on online learning, you have one sample per update, and you can only see it once, basically. So as basically in human brain. And there are many in between in the spectrum, things like mini batch online learning, where you still see the data only once, but you still process it as a batch. There is mini batch incremental learning, where you are allowed to actually repeat over the data. So there are many variations. My interest and research is about online learning end of spectrum, and more specifically online continual learning. So that is basically defined learning incrementally from non-stationary data streams without retraining and without catastrophic forgetting. So how do you do this? So online continual learning tries to answer this. Basically, this paradigm requires model to make predictions and update as soon as each data point arrives. So just imagine a data stream, and your model needs to predict, infer, and also learn at the same time from the stream. So this is the main paradigm. And you may ask, okay, what is the current approaches? Like how the different companies or researchers deal with this kind of issues, this adaptivity issues. So there are two main ones. I would say the first classic one is basically retraining, combining all the new data, creating the new data set and retraining from scratch, or maybe fine tuning. And this can be seen also from the lens of ML ops. Like you train your network, you review it, you deploy it, and it works, it does the inference, but you also monitor the accuracy of this model. And if there is an issue, like a model failure, you have to maybe revert this, or you have to take it offline and collect new data, retrain. That's this blue part, so data preparation, redevelopment, and retraining. So this is an expensive process. It's a periodic, large-scale training. Retraining consumes a lot of energy, compute, and time, basically. And just imagine that you have an inspection drone or robot that you put it into a new environment, you realize it failed, you have to collect data and retrain. So this all means downtime, basically, for any edge deployed AI system. And of course, the scalability under like high velocity data streams is also another big issue. But I hope this is clear, like that this can't be used in all situations. And the other one that is more recent and emerging, I would say, is in context learning in the case of large language models, especially. And this, for those that haven't heard about this, it's when these big models learns new tasks, not by updating their weights, but based on all the samples of the tasks in their context window. So you can think of it as a huge working memory where you learn temporarily inside that context, based on that context. And the problems with this, of course, firstly, it is not permanent knowledge embedded into the model. It's just temporary in that context. It requires cloud scale accelerators, a lot of memory, and it's just for every adaptation, you have to process hundreds of context tokens, basically. So these are the issues. These are the current approaches, and the alternative is basically to do online continued learning and adaptation. So that was the qualitative reasons, let's say. But I also, to fully convince you like that this is really necessary and you cannot always get away with bigger model and more data and more GPUs, I want to show you some quantitative results from literature. And that it is about, this one is about domain adaptation in autonomous driving, where the weather conditions change. Like in this case, there is heavy rain. So the goal here is that when there is weather changes, um, your task is to do segmentation of the images, and you want to keep your performance high. So here in the first column, so these are the first row is the accuracy, the FPS is clear, gigaflops is just the amount of compute needed, basically. So if you take an Oracle approach where you retrain on the old and new data combined, this is what you would get. So this is like baseline, but this is not possible to do in real time while the car is driving. So this is just a reference point. So what happens, and these are segmentation transformers, so these are state of art. What happens if you take model and you not adapt it? It's this second column here with no adaptation. So in this case, we see that without adaptation, you have huge accuracy drop from like 70% to 57%. So this is the problem of environmental changes and not adapting to it. Okay, so then one solution is just to have bigger model and more data now. And we see that, yes, it partially works to have bigger model. This B5 is bigger than B1 model, but you see that firstly, still accuracy is not as good as Oracle. So still there's some degradation, but moreover, of course, bigger models means more compute and slower processing. So FPS drops. And there are many other online domain adaptation methods, but most of them either doesn't have good accuracy or they are just slow. For example, the Kata one has as good as a big transformer model, but its FPS is quite low and it requires a lot of computation. So on this last column, you see another method that actually has all green, so it has good accuracy, but also relatively low computation load. And the way that this algorithm achieves this is by updating subset of the network and also updates only when necessary. So this is critical because this is a hint towards where my thesis also goes towards. Is there any questions so far? So I hope this is a first part of my presentation. So I hope by now you are convinced that some applications need this real-time adaptive AI because frozen static AI is not always appropriate, and that this kind of adaptivity is computationally expensive and is a hard problem. So if there's a question, I think we could stop here for a few minutes.
Dr. Lou, you have a comment. Would you like to elaborate on it? Anyway, you can continue. We don't have a question.
Okay. So the second thing that I want to discuss is that then this type of AI needs actually novel algorithms and specialized hardware. And in that regard, I want to go back to what I just mentioned, that this other work actually achieved this by updating only part of the network, only part of the time. And that is what I want to discuss here, that the classic learning with the backpropagation, which is global learning basically, if you want to update any weight, let's say these are these two blue weights you want to update. To do that, you need information from all the network part of the network that comes before. And you also need to send the information backward, basically, to previous layers. Classic backpropagation, and this lightning science just shows that you synchronously update all these weights all the time when you're doing training. So the local learning from the brain inspiration and neuromorphic computing tells a bit different story. Says that you should do learning only based on local signals. So if you want to update these two weights, you just need the information from these neurons that are synapses are attached to. But still, it is doing the update synchronously for all the weights all the time. So in its classic form. What I am interested in is event-driven learning, where your update still is local, but also event-driven, meaning that only when there is spikes or events on presynaptic or postsynaptic neuron, you actually update the specific weight. So as you can see here, the lightning, which is the weight updates, happens only sometimes and only for some of the neurons. To summarize, basically in global learning, information needed to update a single weight is global, so you need global information. And update granularity is dense, so it's spatially and temporally dense. Local learning, on the other hand, requires local information, while it still happens in a spatial and temporally dense way. And the event learning is local and at the same time spatial and temporally sparse. And this is in line with what previously I mentioned, that if you want to achieve fast and efficient real-time learning, you need to do local and event-driven learning. So update only some of the weights, only some of the times. Now, what I have been doing last 5 years or so in this field is all meant to go towards addressing these questions. So I started with initially working with the Loihi 1. So this was the first generation chips that our lab built quite some years ago already. And initially we looked at this robotic task where the robot looks at the object, as you see in this video, makes an eye movement, and has like this event-based camera that sees the objects like as you see here or here. And the goal was that this robot learns new objects over time. And the paradigm that I have used to make this learning happen is so-called prototype-based learning, where you basically say that in a feature space, I have the samples and they generally cluster around some prototypical representations. So you can imagine that you have like a PC or a cup or a laptop sort of clusters, and the prototype is basically the center of these clusters. And this way you can, when there are samples falling on the empty part of the space, feature space, you can detect them as novel. You can also have multiple prototypes per object. So for example, here you can have multimodal representation. Let's say you have a class of computers, but they are clustered into two distinct clusters, like here laptop and personal computer. So instead of trying to push the model to combine this somehow in feature space, we just decrease its burden and allow it to just assign separate prototypes with the same labels. So this is the paradigm I have generally used in my work. and in this first project, our goal was to do an interactive continuous learning for robots. So like you have a robot, you have a user, user shows some object, robot answers, and blah, blah. And when it makes a mistake, this triggers learning. So that is, for example, about doing learning only some of the times. This initial work had a small network, hand-designed feature extractors, and this so-called prototype network with a bit of complex architecture because Intel Loihi 1 had some constraints, like in terms of how you could implement architectures and learning. I don't want to go into so much detail of it. Just mentioning that this is how one version of the Loihi 1 looked like. And we had like fit this network in this USB stick, basically. What we had shown with that work initially was that when you really have simple objects like a tennis ball or bottle or bowl or orange, you actually required the network automatically allocated just one neuron per object. And if you had the relatively complex, visually complex objects, like that doesn't have symmetries or things like I don't know, a hammer or a wrench, this kind of things, or whatever just looked more complex because of its feature space, automatically allocated more neurons. So this was the first result, and in terms of benchmarking, this was already a couple of years ago that we showed that it gets like 300 times better energy compared to CPU at the time. Execution time was similar, latencies were similar, but it's also because these were super simple networks. Then the second generation of the Loihi 2 arrived around 2021. And this is when I realized that I can do more with this new chip because it had now integer valued spikes. You could have more complex neuron models, like you could program them. Of course, it was just more fast. It was just faster and denser. This new chip, it had better input-output modalities and etc. So that's why I went back to drawing board to design a new algorithm that can leverage this new capabilities of Loihi 2. So if you look into a Loihi 2 chip, you have these neural cores, and inside each neural core you have this SRAM memory array. And next to it sits basically the computing part. So that is the near memory compute technically means. So the interesting part for me here, and what I want to talk today about, is the learning, on-chip learning, and that makes that actually makes Loihi chips quite unique. That they have this on-chip learning acceleration that is very very flexible, that you can define different learning rules and algorithms. So I want to just shortly talk about it, that you can imagine that you have like two neurons, presynaptic, postsynaptic. There is a synapse, of course, connecting them. Presynaptic neuron have some traces. Postsynaptic has its own traces. And basically, Loihi 2 defines the learning based on these traces and also the variables of the synapse, which is like its weight and delay. You can write it as sum of product equations. What this basically shows is that you can define a local learning rule based on your weight and pre-postsynaptic signals. It's exactly as in the computational neuroscience literature. And the critical thing here is that Loihi 2 combines these two types of learning locality. One is hardware level, meaning that the computing logic that updates the weight is next to the SRAM, which stores the weight. So you don't have this memory bottleneck as in GPUs where you have to read and write the large batches of weights from the DRAM to the computing unit actually. So this is one level of locality. The second level is algorithmic for spike neural networks in general, and that is about that information required for the synaptic update is local to the neural core. So it's like different neurons are near to each other. So to update a specific synapse, you can easily access those signals of those local neurons. Based on this Loihi2's learning capability and the prototype approach that came from my previous project, I designed a new algorithm called continual learning prototypes. This is a generic algorithm that actually can be implemented and is implemented in other hardwares. This is different from the first project where we directly built the system on Loihi 1. And instead, in this one, we first developed an algorithm and validated it, and then we implemented it on Loihi 2. But during the design process itself, I always had to keep in mind the constraints of Loihi 2. So in this algorithm, what it tries to achieve is basically that when you have this online continual learning scenario, like you have a robot that looks at the household objects, a video of basically like a live feed of the robot. It sees like a sequence of objects, so that's this continuous stream, and it can make mistakes, and this is for example, you see one object, then you see next object, and when you come back to previous object, if you don't have continued learning, you will forget the previous object. So that's called catastrophic forgetting. So what CLP is about is it tries to solve this problem for online continued learning. And it does this with multiple mechanisms. First is metaplasticity. As in human brain, basically CLP tries to consolidate the useful knowledge and keeps the new or problematic knowledge more plastic. This is how it tries to address the stability plasticity dilemma by with a high granularity, trying to control which part of the knowledge is more plastic, which part is more consolidated. Secondly, we have multivariate modeling of classes. As I previously mentioned, you can have multiple prototypes per class. You have on-demand prototype allocation. So you basically have a lot of free, let's say, memory. And this can be allocated over time as the robot or drone goes around the world and encounters new objects or new versions of the known objects. It automatically allocates over time when see like a novel object. So if you look at the feature space, like this one here, if there is a sample that falls into this empty space, it is detected as novelty detection. So it's very intuitive how this works. It can do also semi-supervised learning. So if there's no label provided, so if the robot is alone or there is no supervision provided, it can actually learn in unsupervised fashion. But when there is directions and labels, it will behave as a supervised algorithm, basically. It can also compensate for concept drift. So let's say um, a concept of an object can evolve over time as you see new examples of this object. And that is what this algorithm can also do. And finally, it doesn't need a lot of data. It gets just with few frames and samples, it can learn new objects. So this is the overview of the algorithm that was developed with the constraints of Loihi in mind, so that we could implement it later on Loihi 2. But it is also it can be run also in GPU or CPU. Any questions so far about the about things I have discussed? If not, I will just continue. So basically, what we have shown with this algorithm that when there is very little or more data in both cases, it actually outperforms the other competing methods, also the replay-based methods, which is sort of generally the golden standard in continual learning. It can actually detect novel classes also with a very good accuracy. I will not stop so much on this ones as we have only 20 minutes left and I want some discussion to happen too. The bottom line is that it has good novelty detection mechanism. And it can also perform quite well when deployed as a semi-supervised learning algorithm. So let's say you actually learn some classes with supervision, and then you see new classes without supervision. In this case, the algorithm itself allocates new prototypes, learn this new object. It just doesn't know the names, basically. So then the user can name or label the learned prototypes, and we can then test on all classes. So in this case, the blue is the base classes, and as you can see, it doesn't almost drop at all from the initial base accuracy, so there's no forgetting. And the orange is the novel class accuracies, learned unsupervised. So as you have more samples of that classes, you can get quite good accuracies, basically. This is a very nice plot that I like to show to give an intuition about what really prototypes are and why they are useful. So this is a feature space that is extracted by some deep neural network of this objects data set that I have been using. And each color is one class. So if you look carefully, you can see that some class has just one cluster, some has two, some has four, etc. So and some of them, for example, for class 4, you can see that it's quite dispersed. So linear or classic classifiers wouldn't be able to classify this well. But if you use prototypes, you can see that it actually allocates as many prototypes as it really needs. So for class 18, there's just 2. For class 4, there's 4. And class 13, for example, has just 1 prototype. So this is the on-demand prototype allocation of the CLP algorithm. So this was like a algorithm development And of course, this as the final phase, we needed to put this into Loihi 2 to show that actually this algorithm and Loihi 2 is a good fit. That has been like since beginning the goal. And we call this version CLP-SNN, spiking neural network, because in the end, neural network architecture is different from the original algorithm in the sense that this one needs a definition of local learning rules and etc. So basically, we keep the learning scenario same, but we develop an SNN architecture and neuromorphic implementation on Loihi 2. So we have designed a new three-factor local learning rule. Again, I don't want to go into mathematical details here, but basically, each neuron has its own control over its plasticity level or its learning rate. So each neuron over time changes its plasticity, meaning it updates slower or faster depending on evolution of this neuron. We use mechanisms like neurogenesis, where you can allocate a new prototype over time, metaplasticity, where different neurons has, again, their own learning rate, and that really helps with the continual learning because we try to protect the useful knowledge by consolidating it. And altogether, this ended with an architecture called CLP-SNN. That is shown here. Basically, you have input neurons, you have prototype neurons, novelty detector, and modulator neuron in general. So when none of the prototypes spikes, given an input, we basically detect it as novelty, which then sends back as a modulator signal to allocate a new prototype. Or if actually there is a prediction, this goes to a supervisor that provides a feedback about the prediction, correct or incorrect, which in turn also updates the neuron that made the prediction. With implementing this algorithm on Loihi 2, we showed again that it actually outperforms the same competing methods when it's also implemented in Loihi 2. Here we show, like, as you learn new classes, so in this data set there were like 40 classes, as you learn new classes, how test accuracy on previously seen classes changes. So let's say if you have learned 2 classes, you test only on 2 classes. And if you have learned so far 10 classes, you only test on those 10 classes, not all future classes, basically. So this is like a natural way you would actually evaluate such algorithm. So as you can see, if you have like fine tuning, which is just updating without any continual learning method, you get catastrophic forgetting, that over time you lose accuracy quite a lot. While continual learning methods, including CLP, has keep quite a lot of accuracy. Of course, there is some decline, but this is not because of forgetting. It's just because the task gets harder. Because in the beginning, it's just classification of 3-4 classes, and then towards the end, you have actually 40 class classification problem. So if you have more data, like if you learn all the classes and then you go back to those classes to learn them better, that is shown with this 25-shot learning scenario here. Here there are other methods that performs a bit better than ours, but in terms of then latency and energy, our method is significantly better, especially compared to this SLDA, which is the method that performs a few percent better. Our algorithm on Loihi 2 basically has 70 times lower latency and more than 5,000 better energy. So to get few percent of accuracy, you have to give up a lot on the other metrics. Or you can use very simple method like nearest class mean classifier, and then compared to that, our method is like 70% higher accuracy. So to see them maybe in more visually clear way, I have here the Pareto frontiers. On x-axis we have accuracy, on y-axis we have energy efficiency of the learning for different methods and on different hardware. So if you, and these are log-log, of course, log versus linear. So if you look at the other methods implemented on Loihi, implemented on CPU and GPU, the green, red, and orange, you see that they fall on a line, and this is the Pareto frontier of the efficiency. So to get the better accuracy of SLDA, you actually need to, you get the basically lower energy efficiency. So you need more energy for each sample to learn those samples. So this is the Pareto frontier. And we see that the CLP algorithm itself implemented on CPU and GPU is already improving the this Pareto frontier. So this is the original Pareto frontier, and this is what CLPs look like. But if you actually take CLP and implement it on Loihi 2, then you get much even further gains in terms of energy efficiency here. So that's the star is the CLP on Loihi 2. Similarly, if you look at the learning latency versus accuracy, you can see the same pattern that the other methods fall on a Pareto frontier. Our algorithmically already improves the this frontier, but then implementing it on Loihi 2 brings even more efficiency and speed. Of course, there's a little accuracy drop because of the fixed point nature of Loihi and other constraints, but that is exactly what Pareto frontier is about. That we look for the best optimal trade-off of efficiency and performance. So to conclude, I want to come back to my original argument that online continuous learning, lifelong learning, real-time adaptation, these are very compute-intensive tasks, even if it's about a single layer being updated. The second conclusion is that CLP and Loihi demonstrate the value of the in-memory computing and the locality of the learning. We saw that when the algorithm and hardware is co-designed for locality and event-drivenness of learning, we can actually break this Pareto frontiers of the classic methods implemented on CPU and GPU. Of course, there are still limitations, and that is what future work are always for. So, so far my work has focused on learning on a single but complex layer. And this has, of course, its own limiting performance. So we need to scale this to even deeper network. But I think already the task scaling is quite good. For example, like this 40 classes of objects in real world environments with all type of variations. But still, I believe that single layer learning is not the final answer. We need to have also deeper updates when it's needed. One big, let's say, concern with the adaptive AI and continuing learning is that how do we guarantee some performance and certify this models for future? So this is still an open question. So for me, the future is about trying to answer exactly what applications would benefit most from such real-time learning systems. I have had many discussions over years with so many different researchers about this, and there are many ideas. And nowadays, I start to even see startups, especially in US, popping up with the promising to do this adaptive learning and etc. So I think now more and more people realize that this is actually needed and we can't go on forever with the static models. But of course, exactly which applications is still an open question and we need to answer. So that's it from me today. I hope I managed to convince you. And if not, I'm open to questions and comments. And thank you very much for listening.
Thank you very much, Elvin. A great presentation, really, and timely one.
Thanks.
We have few comments and questions from Dr. Lou. If you can please.
I need to see if I can see the. So I think first first comment was about MLOps. You want to mention this, Professor Lee, yourself, please? You can also unmute.
Sorry for the distraction. The first comment, I think it's irrelevant now because I was just joining a bit late and I see your focus was actually not about the ML ops. It was just a comment that depends on which machine learning model you are basically running. You don't have to retrain at all. But in your case, I think it's irrelevant because you have already a very specific case of the machine learning models that you are focusing on, and we can then move on. I would like to know, first of all, thank you very much for the talk. That was very inspiring, because I was interested in finding out whether this spike neural networks might improve the current challenge or solve this current challenge on the energy and in particular also the scalability of the current other trends, mainstream transformer-based architecture. And I was a little bit frustrated when I started learning into it, and then discovered and find out that we have a big challenge on the case when it can't really scale very much, and I have to limit myself on the very small use case like event-driven use cases. Also, I see a lot of challenge on the latency part. So that is basically my major question today. So do you have any kind of a benchmark showing how it's tackled the latency challenge? Because on your page number 26, I've tried to find it out, and you have mentioned that latency comparison, but I don't see the latency values.
It's here.
It's
here.
Here.
It's just a very dense table. So on the other one, I focus on priority frontiers, but this is latency value. So this is like a 1,000-dimensional feature vector learning, basically, and it's purely about learning latency of that single sample. So, for example, in Loihi, you can do it in 300 milliseconds, let's say. 300 microsecond, so less than a millisecond. And you can see the other values for GPUs and CPUs. And GPU here is the NVIDIA Jetson Orin Nano, so Edge GPU, of course, because we are targeting Edge, so that's the, let's say, competitor, and its CPU. You can see that there is like at least an order of magnitude difference with the other methods. NCM is a bit of an outlier here because it's very, very basic algorithm. Still useful at the times, but the accuracy is significantly lower than others. But that one is just basically vector-vector multiplication and nothing much more than that. But if you look at more proper algorithms like SLDA, you see that there's really, one or more.
Promising.
Yeah.
Yeah. Thank you. I will take a look at this. Do you have a paper here?
Yeah, it's this
okay,
one.
perfect. I will take a closer look at this paper. Thank you very much.
All
for
the
direction.
details are in this paper in terms of comparing. So it is, we designed this benchmark exactly for this purpose, to do cross-hardware, but ISO algorithm, ISO task, but also purely ISO task if we look into other algorithms too. Like the goal is, for me, the really nicest result is this, to show that to get to better accuracy, you lose energy efficiency and you lose latency. You gain more latency. So there is this really frontier, and which makes sense. But it also shows that with proper advancements in the algorithm itself, which in this case is about event-driven learning, meaning that you only update a part of network only some of the times. Then you already get, by algorithmic advancement, you break out of this frontier. But then if you also combine it with the hardware that fits to the purpose or fits to this algorithm, then you actually get even bigger jump in the efficiency. So of course, at that point, when you change the hardware, you don't aim for getting higher accuracy. You aim for just to speed up and to decrease the energy. So that's what we have shown basically with this work, benchmarking.
Thank you a lot. I don't want to keep the session all about my questions. I would like to maybe first let other participants raise a question and then come back, because I do have follow-up questions.
Of course. Thank you.
So
Thank you.
I have a question, Elvin. When we will start to see this Lohi 2 with continual learning deployed in AI factories at scale?
Yeah, hard to say, of course. I mean, it's I think it still looks for its use cases. I think it's also, of course, matter of what the mainstream AI research, in which direction it goes. So there is no easy answer, unfortunately. I think, of course, I believe that if there would be more mind and financial power invested in this kind of directions, we would see more results and faster adoption. But it is challenging. It is challenging to do co-design of algorithm and hardware, but it is where the value lies. And I think as there is more AI around us, I think we have been hitting the energy and latency bottlenecks already with the current foundational models and everything. And I think that will push, and I think that is pushing people to think about actually efficiency and speed and this co-design. So even though the mainstream looks like following a different direction, I think the challenges that will come out of it and will define the future of neuromorphic. I have seen already many of the neuromorphic ideas being rebranded in a different way and made part of other type of hardware and algorithms. So that already says a lot, I think, about
Yeah,
what
so it is still in research phase. And if we talk
I think
about
there are some. I would say there are this. If you search for what was the name? Data flow architectures, data flow hardware architectures. You would see that some of these ideas are already commercialized. It's just not under the name of neuromorphic, I think, at this point. There are different names there, and it doesn't maybe use the brain inspiration part. It doesn't use maybe the spiking part, but for example, memory, near memory or in memory compute is very important and is actually being commercialized. Sparsity is another big deal, which I haven't explicitly mentioned, but it is the exact thing that I said, like only some part of the network is updated and stuff like this. So I think it is being commercialized under different names and different parts of neuromorphic, but maybe not in its original form, which is also already a very debatable thing to discuss, like what is original neuromorphic. A lot of people would also say it's analog and digital chips like Lohi is not really neuromorphic or so I don't know. There's no simple answer, but I think part of it is being
yeah,
commercialized.
because if you Bill Daly, the chief scientist in NVIDIA, he said even current new AI implementation based on neural networks, it is still brain inspired. So, and neuromorphic
Yeah, of
computing
course.
is also brain inspired. So, what is the major big difference?
It's always a spectrum. No, it's a matter of like which ideas you try to translate from brain into into technology. Of course, the neuron itself, in its basic form, is bio-inspired, but now it has really abstracted away and went away from um, brain inspiration or backpropagation, which is the backbone of the training of the networks. Is has been shown that is not really plausible in brain, or it's not the way that brain learns. But we still everyone uses it because it solves the task of getting this network and having your input output data and basically training that network to represent that data. So um, it's always a spectrum of bio-inspiration, I would say.
Okay, so Dr. Lou, you can continue because I don't see questions from anybody else.
I see something from Miguel. If you're online, you could maybe speak up.
Who is this?
Hi, yeah. I was just extremely curious. Thank you for your
Miguel.
presentation.
Okay, Miguel. How are you, Miguel?
Yeah, great, great. What about you? I thank you so much for your presentation, Albin. I
Hmm.
didn't
Thanks.
know much about neuromorphic before it, so that's kind of what I joined to learn a little bit more about how it works and the
Mm.
benefits for the industry, because it's true that we're kind of getting to a limit on the power, right? And power consumption and efficiency of training AI. So I believe this is a great solution based on what you said. And I saw one of the slides that you showed. It was like a great improvement from the first version of Loihi to the second one. And I was just curious about if you guys are working on like even more powerful versions of Loihi.
Yeah, of course. I mean, the architecture and hardware development is constantly happening inside the group. So at some point there will be a newer generation. It's just a natural continuation of the hardware development. But when and in which form, I cannot say right now. I don't think it's also quite
No,
nailed
of
down.
course, because it's interesting because this is at least from what I understood from your presentation, this is a very vertical integration, right? From
Yes.
the hardware design to the algorithms to everything that you guys are working all together to design this, I guess.
It is. It is. That's the whole idea. Yeah. In our team, we have like from low-level hardware design through the embedded software, and then algorithm and application design. So it's a fully vertical approach to tackling this problem. So which has a great potential, but it's also a big challenge to tackle in general.
Very interesting approach. Thank you so much for your presentation. It's
Thank you
really
for
helpful.
listening.
Yeah, thank you.
Okay, Dr. Lu, if you would like to continue your questions.
Yeah, thank you for the chance. My follow-up question is, if I understand correctly, in your talk, you mentioned two major novel fix or more novel improvement in your algorithm to fix the catastrophic forget. One is the metaplastic
Plasticity,
weights, and another one is this prototypes that you
yeah.
add.
Mhm.
And both of the, so first of all, for the metaplastic weights, don't we have to introduce another additional overhead to remember or control that weights? So where do you do that? Do you do that already on the Halloy 2 on the chip, or do you solve it software method on
Mhm.
another way? Yeah, not hardware but software. And what about the prototype? That part I don't fully understand, to be honest. How can you dynamically add a new neuron? Do you encode that neuron somehow in another representation way because the hardware is already fixed? So, I mean, the neural architecture is somehow
Mhm.
dynamic, if I understand, but how do you represent the dynamic neural architecture on your fixed hardware?
Yeah, definitely very good question. So metaplasticity is done on hardware. That's actually one of the core things, and it is part of the neuron model. So the neuron models are programmable. So and they are like this stateful neurons. Like if you have the basic spike neural networks, you have voltage and current, let's say, So in this case, this neurons has voltage and current and other things, but also has this metaplasticity level or plasticity level as a variable. So you can think of it, if you're familiar with the computational neuroscience, for example, there's this uh, calcium levels inside the cell, inside the neurons, and that is thought to be controlling also the level of plasticity of that neuron and etc. So you can think of it like that this neuron has a variable that is its learning rate, its own learning rate, and this when the weight is updated on the chip, it basically has access to because it's the postsynaptic neuron, so it's a local information. So you can actually this weight update rule has access to that neuron's learning rate. So that is how
I got it. Yeah.
exactly this happens. So if you look at the this learning rule here, you have this alpha, and you see that it depends on the K, which is the neuron index, and this is stored inside that neuron.
Your
And
constant read. You
yeah,
have a constant read because you have already encoded in the current accessible memory set that
yeah,
assigned to that neuron. So that's the efficiency gain, right? Okay, got it.
yeah,
Thank you.
yeah. So the neuron model anyways executes when there is a spike, and when it executes, it already reads all of its states, and these are in the SRAM next to the compute. So this is the fast and efficient part of the thing, basically, and it's used in the wait update.
So, Elvin, how you then create neurons dynamically? Maybe I missed this one.
No, I was coming to that. So in reality, of course, Lou is right that the architecture is fixed. So you need to define in the beginning how many neurons you will have. And that's exactly what I also tried to describe here. That you have the strapped neurons that is originally allocated. Like, let's say you have 1,000 neurons that are allocated there. It's just their weights are zero, basically. It's just when they receive this allocation signal from this novelty detector, that they detect there's novelty, and this novelty detector's signal goes back to the population, and this triggers one of the unallocated neurons to learn the current input, basically. So that is how architecture evolves, actually. So, of course, practically they are all allocated. They are just inactive. They don't perform any let's say, computation.
But how you know that you need 300 inactive neuron that you might need in the future to activate?
Yeah, of course. I mean, in that regard, you need to put a limit, and that depends on the task, like how complex of a task you are gonna deal with. But you can't also have an unlimited number. So I guess if in the worst case you just put maximum you can fit into the chip, and then you sort of recycle the other neurons. That maybe you have some neurons that are not being used anymore. They have been allocated and learned, but they are not useful anymore. So you can recycle the old knowledge. It's the same thing as in the brain. It's you need to recycle some of your capacity as you learn new stuff, like by forgetting some of old but useless things.
Yeah. Can we do this now when we have
That
GPUs?
conscious forgetting or useful forgetting is not implemented yet, no. But it's pretty straightforward, actually. It's just I haven't focused on that so much.
So if it can be done with the current GPUs, then why do we need a new chip like Lohi to do it?
So the idea that I try to convince is that we to get fast and efficient real-time learning, you need both spatial and temporal sparsity, meaning that only some neurons update some of the times. And in that case, GPUs doesn't make so much sense because GPUs does dense processing with the batches of the data. So even if you try to make it sparse, it will still compute everything, and that will not bring so much gain. So you need a hardware that is capable of leveraging sparse learning, and this requires on its own this memory compute integration, because when you have to communicate a learning information from further away parts of the network, this requires a lot of information passage basically from different parts of the network. But if you have local learning, you can access the nearby information. But again, this is an algorithmic idea. But to really leverage it on the hardware, you need to have the hardware that's also has this memory compute integration. So to summarize, there are maybe three key categories of let's say advantages. One is sparsity of learning. This requires an hardware that actually can leverage that sparsity. Second is memory compute integration, which goes hand in hand with the locality of the learning. Again, that requires that kind of new hardware because GPUs doesn't have this memory compute integration. They still have a long distance between memory unit and compute unit. And the final one is event drivenness. So you only compute when there are events. Like you only learn when there's an error on a specific part of the network, not all over the network all the time, but only at specific parts at specific times. This brings the efficiency, but you need to have the hardware that actually can leverage that ideas. I don't know if it was clear.
Actually, it's very good. So we can summarize the advantage of neuromorphic computing hardware is sparse computing, right?
Yes.
And in-memory computing, right?
Yes. And event-driven computing.
How about energy saving or efficiency?
That is the that's the result. That is the outcome of those advantages, basically.
Yeah, that's excellent actually. And the current hardware doesn't support any of this, so we need neuromorphic computing hardware. But when we'll really see it deployed, that's the question. That's really the main question now. Like Lohi has been there, but I don't see large market for it.
Yeah, because it hasn't reached the productization level yet entirely. So it needs to reach there, but to reach there, it also needs appetite.
I would like to add this part about the use case because you have just mentioned one of the key benefits is the event driven. And event driven for me, it means, okay, you have the optical flow, you can detect the optical flow change, and you basically are driven only by the optical flow stimulus from the perception in your sensor, and you can work on that. And that is obviously, I mean, not obviously, but it's a very famous advantage that we now know, and we see a lot of promising outcome from your lab. That's why I come into at all into the spike neural networks field to read about it. But what other use cases are you familiar with, or can you now currently or your lab are imagining where we can use it? Because I see also from many kind of a news, I see, okay, you try to combine this Halo 2 chips to a robotic for maybe moving some basic movements of a robot and so on. Is there any other kind of a deployment, in particular in the direction where IoT or wireless sensor networks can be combined with the benefits of this kind of neuromorphic chips?
I mean, one of the most intuitive and my favorite applications, at least in my intuition, is also connected to IoT, is this predictive maintenance things that you have actually in factories now. You have more and more sensors, and you need to process them in real time, and they change also. Like there is the sensor drift, there is new anomalies happening, and you would like to keep learning this in real time so that you can actually predict that something will go wrong before it goes wrong.
Yeah,
So
perfect.
this is a one area that I see a
Predictive
future.
predictive maintenance.
But yeah,
Predictive maintenance, right? Okay.
yes.
Predictive maintenance. That's a very good point. And my maybe final question is, do you see any kind of a challenge or open research direction in the sense of combining your current algorithm or examine your current algorithm regards safety? Because I'm rather from formal verification, and I see there might be a challenge or some case where if we take a look at the predictive maintenance case, right? In the predictive maintenance case, a failure is less acceptable than other cases where, well, if there's 80% accuracy, we can basically accept that. Yeah. But if we miss out any kind of a case, then it's a big issue. Uh, do you see some algorithms challenge in your case that maybe there are some kind of a application of symbolic reasoning or neural symbolic reasoning where we can work on?
Yeah, I mean, I mentioned it at the very end of the limitations that I think this is one thing I have heard a lot. Uh, Safety critical applications like autonomous driving. Do we really want to make the models adaptive and things like that? Which is very fair and correct question. I Yeah, I mean, I have a bit of contradictory intuition. I think
Mhm.
in a way, being able to adapt your network, as long as you have verified this learning algorithm under different novel conditions, that how it reacts to novel conditions, I think
Mm.
it is actually more useful or more safe to use it rather than relying on a static AI, which you never know how it will really react to when it encounters an unknown situation, I would say. But I'm also really far from the safety, critical applications, and the certification of neural networks, explainability. I'm really far from these fields. Uh, but I think if you have adaptive AI plus explainable AI, like for example, prototypes are very intuitive. I mean, they really mean something in explainable way. If you can combine these two, uh, I think actually adaptive, I would say, is more safe. I mean, just imagine, like, would you trust your autonomous driving car more if you would know that it would adapt in a different weather condition, if there is more rain or fog or something, than otherwise? I don't know. It's a bit of
Mhm.
a hard question, but my intuition tells that is needed, because that's also what humans and animals do. This domain adaptation, domain incremental learning is, if that was if you wouldn't need it, humans wouldn't have it either. Like, humans would also just stop learning and adapting, I don't know, when they reach 20, or when they really finish their development, they would just stop learning and adaptation in total. So if humans and other animals has somehow conserve this ability of adaptation, I think it has a value in real world deployment or real world AI, let's say.
Thank you for your insight. May I just close my thoughts on this question, or rather direct this in the opinion of network deployment. So far, if I read your current outcome, it is rather one chip rather than multiple chips. So have you imagined or worked on any kind of a use case or scenario where you have deployed multiple chips working together?
No, no. I
Okay.
there is a lab that uses this algorithm for federated learning.
Yes.
I guess that's what you're alluding to. Uh, I forgot the name of the lab though. It's also in Germany. Not public. I think not. It's not published yet. But
Mhm.
they try to do exactly that. That they have like a
Okay.
different robots learning their own prototypes, and then at some point they sort of merge in this federated learning scenario. But I haven't
Sounds interesting.
worked myself on.
Okay. Thank you very much. A very
Thank you
inspiring talk.
Thank you,
for
Dr.
all the
Blue.
discussion.
I have lost a question before we leave
Sure,
because take advantage of your knowledge, Elvin.
sure.
Imagine, you're familiar with autonomic network, which is self-managed network, like can be enterprise network, carrier network, broadband network, you name it, which has
Mm-hmm.
switches, routers, firewalls, whatever. And autonomic network is a network that manage itself. It is self-management, like
Mm-hmm.
self-healing, self-configuration, self-optimization, and self-protection or security or defense. If you would like to implement or develop such a kind of network using agentic AI, then you need adaptive continual learning because the network condition change based on traffic, which in user availability, user behavior, you name it, right? So
Mm-hmm.
I would see, correct me if I'm wrong, that's a good application for neuromorphic computing, continual learning, right?
Um, in theory, yes, but in practice, the the problem is always like now there's like there's so many layers of applications application layers. Like if you reach the agentic AI level, let's say,
Yeah.
below that you have so many things, like you have foundation models, and foundation models require transformers, and transformers require matrix multiplication, and then matrix multiplication is something what GPUs generally do very well, but it's not really the strongest part of the neuromorphic chips, for example. So there are like these different levels of abstraction, and agentic AI and the application of it is on the top layer, but there are so many layers below it, and to enable all of these layers in neuromorphic hardware is the challenging part, like uh, because that's the mainstream AI's, I think, advantage is that it co-evolved together with the GPU hardware architectures and CNNs and then transformers and then like so much investment and so much money and brain power on this that they and plus the PyTorch and all the other infrastructure going behind. So there's so much um, going on there and co-evolving that neuromorphic has its own sort of ecosystem and is trying to integrate into these other things, but they are not necessarily always compatible. That's the challenge. So even though in theory, yes, I think in practice there is still a long way to reach that level of like saying that I have an agentic AI, let's just run it on a neuromorphic chip. This is the um,
I got
the-
it. So,
yeah.
there is no money to develop all the neuromorphic chips to have all these capabilities we have in AI now. There is no, the ecosystem is not as large.
Yeah,
So the money is not the same, it's not available for neuromorphic. Most of the effort, people, time, money is
yeah,
devoted to the current system, transformer, blah, blah, blah.
yeah.
So using agentic AI for autonomic network would work with existing system based on all these abstractions. To run it on neuromorphic hardware is not possible now, but maybe in the future when the money is there, the ecosystem is there, and
Yeah, ecosystem infrastructure, all the
exactly,
open source developers and everything needs to be there, needs to evolve and grow.
exactly.
Um,
And that is not
yeah,
happening now. That is not happening now.
not in a speed that would allow us, let's say, in a year to have, I think,
Exactly.
agentic neuromorphic AI. I think let's
Exactly.
just
Exactly.
summarize it in that way,
Yeah,
not that fast.
that's a very good summary. Exactly. And do you foresee that this will ever happen?
Uh, I believe that it will happen, but in which form, I'm not sure. As I said, there are a lot of signs that it's also just
Right.
being absorbed, like some ideas and pieces of neuromorphic hardware and algorithms being absorbed by the parallel ecosystems.
Yeah.
Uh,
Or maybe initially we can have some functionality done in neuromorphic and the rest is done the way it is done now. Just not like an assistant to what is happening now.
yeah, I mean, it is, I think, clear at this point that it's never gonna be only neuromorphic, and no one is,
Yeah.
anyways, I think, claiming that or wanting that. It's just it's a complementary thing.
Mm,
Back propagation also will not just go away because we have some kind of other type of Kantian learning,
yeah,
and it shouldn't. So yeah, it's a matter of finding the complementary pieces.
exactly. So current GPUs use backpropagation, but how we can replace it with neuromorphic
Hmm.
learning algorithms and hardware, that is still an area of research, right?
Yeah.
Okay, thank you very, very much, uh,
Thanks,
Irvin,
Bisham. Thank you.
for your excellent presentation and for staying with us for almost 40 minutes more. And the
No,
rest,
it's I enjoyed a lot also the discussion. I'm always happy to have this. It's very valuable to hear from, um, especially from the people that is not directly in the neuromorphic field.
yeah,
So yeah, but thanks for everyone that joined and had listened to this. Um, yeah, hope to see you in another place, I guess. And
thank you
thanks for
very
the
much, Irvin.
invitation.
Can you please send me your presentation slides?
I will check this with my lab. If
Yes.
I get okay, I will send it. Yeah.
Thank you very much and have a nice
Thank
day. Thanks
you.
to everybody and have a great week.
Thank you. Thank you very much, everyone. Bye
Bye.
bye.
Bye.